Have you ever, used an AI assistant to write something,
Yeah.
maybe an email or a project report or, some code, and you just marveled at how impossibly fast it works?
Oh, yeah. It feels like magic at first.
Right. But then later on, you realize it created this completely unnecessary, just complicated mess.
Yeah, that happens a lot.
You look at the output and think about how incredibly detailed the response is, while simultaneously realizing that it entirely missed the actual point of the assignment.
It really represents the defining paradox of our current technological moment, I think,
Mm,
because we have these tools that are capable of generating volume at, unprecedented speeds. And the assumption is always that this volume equals productivity.
right, more is better.
Exactly. But in reality, that unchecked volume is often the exact source of systemic problems.
Yeah, and that dynamic is the focus of today's deep dive. We are looking at a really fascinating case study from 2026 by a developer named at Look036.
Yeah, the presentation is titled Eliminating AI Generated Code Debt, the Node Pairs Refactor.
Right. And it's essentially this slide deck that breaks down in forensic detail what happens when an AI writes code that technically functions, but completely misunderstands the structural architecture of the project it's working in.
It serves as a perfect microcosm of a much larger issue in software engineering right now. We're moving beyond the era of just isolated bad code and entering this era of architectural rot.
Architectural rot. Wow.
Yeah. It happens when we allow an eager machine to just, generate parallel systems way faster than human reviewers can comprehend the long-term implications.
So, our mission today is to really unpack this specific case to understand those hidden costs of AI generated duplication. We want to explore why adding more code isn't always an upgrade.
Usually it's not.
Right. And why, in many scenarios, the absolute most powerful enhancement you can make to a complex system is simply hitting the delete button. Okay, let's unpack this. Let's start with the backstory and how this specific tangle of code was created in the first place.
Sure. So the setting for this case study is a C++ code base called the DiGraphXCP project.
Okay. It's a software library specifically designed to deal with directed graphs. And for anyone not, elbow deep in computer science every day, a directed graph is essentially a way to model relationships.
Like a city map, right?
Exactly. Think of a city map where the intersections are the nodes and the one-way streets connecting them are the edges.
Got it.
Now, within this project, there is a specific component called the neg cycle finder.
A tool for finding negative cycles. Which, going back to our city map analogy, would be like finding a specific loop of streets where the total toll you pay to drive around them is somehow a negative number.
Right, exactly.
You'd essentially be making money by driving in circles, which, is a concept used heavily in things like financial arbitrage or network routing. So a developer used an AI agent to add some new functionality to this neg cycle finder.
Yeah, they needed the finder to process these cycles in a new way. And what's fascinating here is the critical failure point is rooted in how a graph fundamentally works.
Okay, how so? Well, a graph, by its very nature, already stores all of its edge data in what is called an adjacency structure.
Right.
The connections between the nodes, those one-way streets, they already exist in the memory, and they hold all this rich native data about the relationship. The AI was tasked with interacting with this structure.
Okay.
But instead of utilizing the graph's existing native edge data, the AI invented a brand new, highly redundant method. It introduced this pattern it called node pairs.
Wait, let me make sure I'm visualizing this correctly. The AI looked at a fully realized data structure, like a complete map of streets with speed limits, lane counts, toll prices,
Yeah.
and it threw all of that context out the window.
Yep, completely ignored it.
And it decided to build a synthetic pair of generic coordinates like a U and a V completely from scratch.
That's exactly what it did. It stripped away all the rich native context of the edge and reduced it down to a rudimentary detached coordinate pair. It built a parallel representation of data that the system literally already knew how to handle natively.
That is just such a strange approach. It makes me think of hiring a contractor to build a pathway from the entryway of a large office building to the kitchen.
Okay, yeah.
And the building already has a wide, beautifully designed, well-lit central hallway that connects everything.
Right.
But the AI contractor doesn't bother to check the blueprints.
Right.
So instead, it just smashes a hole in the wall to build an entirely separate, slightly narrower hallway right next to the main one, winding through the exact same space. And it labels both of them path to kitchen, leaving everyone in the building just utterly confused about which one they're actually supposed to use.
That is a perfect analogy. And the thing is, the AI didn't create this redundant pathway maliciously.
Right.
It did it because it fundamentally lacked the global context of the code base. AI coding assistants, they operate within these restricted context windows.
Ah, right.
They look at the immediate localized problem placed right in front of them, and they solve it using generic brute force patterns they've seen millions of times in their training data.
So they're acting as hyper-localized problem solvers, completely blind to the fact that they are operating inside a carefully designed pre-existing architecture.
Exactly. The AI recognized a generic problem connecting 2 points and applied a generic solution creating a node pair.
Yeah.
It lacked the capacity to pause, pan out, and ask, does this specific C++ graph library already have an elegant mechanism for yielding this data? It just, started hammering up drywall for that second hallway.
Wow. So now that we understand the mechanism behind the AI's mistake, we really need to explore why this extra code is actually a massive liability. Because at first glance, a listener might think, well, the AI built it the second hallway. It works. The code compiles. Who cares if it's a little messy? The house still functions.
Right. But in software architecture, that second hallway is never free. It has a huge ongoing cost.
Here's where it gets really interesting. The source material highlights this concept called the ponytail principle, which essentially states the best code is the code never written. And when you look at this case study, that principle feels incredibly prophetic. So aside from taking up a tiny fraction of a kilobyte on a hard drive, what is the actual tangible harm of this parallel hierarchy? Let's talk numbers.
Well, the case study breaks down the exact numbers, and they are highly illustrative of the problem. This AI hallucinated parallel architecture resulted in 6 entirely duplicated methods. 6. It generated functions with names like relax node pairs, is negative node pairs, cycleless node pairs, and it wrapped them all up in a method called find neg cycle.
So it just kept compounding the error, building more and more infrastructure to support its initial bad assumption.
Yeah, it required all the supporting infrastructure. And to validate those 6 redundant methods, the AI also generated 2 entire test files.
Oh, wow.
One of those was a massive 113-line file dedicated exclusively to testing the logic of these node pairs.
So we are looking at roughly 467 lines of code in total. And for everyone listening, those 467 lines provide absolutely zero new functionality to the end user of the library.
None.
Zero.
They simply replicate poorly what the native edge data structure was already doing natively.
It is pure, unadulterated duplication. And the harm manifests in 4 distinct compounding ways.
Okay, let's go through them.
First is the ongoing maintenance burden. Code isn't static, right? It requires constant upkeep. Every time a human developer finds a bug in the native edge logic, they now have to remember to apply that exact same bug fix to the redundant node pairs logic.
That sounds exhausting.
It is. Every new feature requires 2 separate implementations. Code reviewers are forced to check 2 paths instead of 1. It effectively doubles the surface area for human error.
You're basically forcing the development team to maintain 2 competing realities within the exact same project. Precisely. Second is the severe cognitive load placed on the developers. Imagine coming into this project as a new hire. Your task is to find a negative cycle in a graph.
Okay.
You look at the documentation and you see 2 distinct options. A native method returning an edge, and this find neg cycle method returning a pair of nodes.
And you have no idea which one is right.
Right. You have to stop your actual work, dig through the source code, and try to decipher the difference. You burn valuable mental energy trying to understand why both exist, assuming there must be a good reason, when in reality you are just reverse engineering an AI's hallucination.
You're treating a machine's mistake like it's an intentional design pattern. That's rough. What are the other 2 harms?
The third is API pollution. The public interface of this library now presents 2 ways to accomplish the exact same task. Users downloading this library will inevitably get confused.
Oh yeah, they will flood your GitHub issues and community forums asking which one is the correct method.
Exactly. And worst of all, it becomes incredibly difficult to deprecate the bad version because the AI pushed it into the code base and external users might have already started relying on it.
Right. But wait, let me push back on you here though. Let's look at that 4th component you mentioned earlier, the tests.
Okay.
You pointed out that the AI wrote 113 lines of tests specifically for the node pairs. If the AI wrote comprehensive tests, isn't that technically a safety net? I mean, fully tested code is usually considered the gold standard.
It is usually.
It feels a bit like, hiring a private security detail for that redundant hallway we talked about. Even if the hallway is completely unnecessary, you've got highly trained guards pacing up and down, making sure it's secure. Doesn't that make it safe?
That perspective is a very common trap in modern development, and it's exactly what this case study warns against. The concept is known as test debt.
Test debt.
Yeah. You have to remember that tests are themselves code. They are not magic shields. They have to be maintained, updated, and executed. Having 2 extra test files means your continuous integration pipeline, the automated servers that build and verify the project every time a change is made, takes longer to run.
So you are burning actual server compute time and developer waiting time on an illusion.
Exactly. You are paying the salaries of that private security detail to guard an empty, useless hallway. And more insidiously, by rigorously testing bad architecture, you cement it in place. You give it an unearned veneer of legitimacy.
Oh, wow. So by writing tests for its own bad code, the AI essentially poured concrete over its mistake, making it structurally sound and infinitely harder for the human developers to dig out later.
Yes. It validated its own hallucination and dared the humans to question a suite of perfectly passing tests.
That is a deeply frustrating paradox.
Hmm.
The tool meant to accelerate the team's development actually trapped them in a cycle of maintaining useless infrastructure. But thankfully, the slide deck doesn't end as a tragedy. It moves into how the developers actually fixed this foundational rot. Which brings us to the concept of subtraction as a feature. The solution wasn't writing a better prompt to make the AI generate cleaner node pairs.
No, not at all.
The solution was discovering the architecture that already existed.
Right. The human developers looked closely at the neg cycle finder component and realized a superior mechanism had been sitting in the codebase all along. It was a native method called Howard parentheses, or just, the Howard method.
The hero of the C++ library.
The unsung hero, really. The Howard method utilizes what is known as a generator-based approach. Instead of stripping away data, allocating new memory, and returning massive arrays of synthetic pairs, it seamlessly yields cycles of the native edge data one at a time.
Now, for those who aren't deeply embedded in software architecture every day, what makes a generator-based method so much better in this specific context?
Think about memory allocation. A traditional approach might be like a chef cooking 1,000 appetizers, placing them all on a massive banquet table, taking up the entire kitchen, and only then calling the waiters to take them away.
That requires massive overhead.
Exactly. A generator-based method acts more like a sushi conveyor belt. It processes one native edge, yields it to the caller, and moves to the next. It requires almost zero extra memory allocation. It is highly efficient and operates in perfect harmony with the underlying graph structure.
Okay, I love that analogy. But the slide deck mentioned that the codebase interacts with several very different types of graphs. How does this native approach manage to handle all those different structures without writing unique redundant methods for each one? Because that seemed to be the hurdle the AI stumbled over.
And this touches on the brilliance of the existing human-designed architecture, specifically a mechanism called edge-type deduction.
Okay.
The original developers had built a polymorphic system designed to intelligently adapt to whatever data structure it was handed.
Break that down a bit. The source material lists a few distinct types of graphs they were dealing with.
Yeah, let's consider the variations. You might have a simple digraph S where the adjacency structure is just a basic dictionary mapping to an integer.
Okay, so the edge is simply a number representing a weight.
Right. Alternatively, the program might be interacting with a pi:::dict structure passed down from Python. Or it could be processing a highly complex unordered map containing custom data objects.
Those are fundamentally different ways of storing information. I mean, an integer is simple, a custom object is complex.
They're completely different shapes of data. But the native architecture handles this elegantly through existing helper functions, specifically things called getable helpers.
Okay.
These helpers are designed to look at the graph type dynamically and deduce exactly what an edge is supposed to look like in that specific context.
So the system acts like a universal translator. Whether the edge is a simple integer or a massive custom object, the getable helper seamlessly extracts the necessary information without forcing the data into a generic, clunky format.
Exactly. No duplicated logic is needed. The system was already built to be incredibly smart and adaptable. The AI simply wasn't capable of comprehending that the system was already smart.
Right.
It opted for the lowest common denominator, stripping everything down to basic U and V coordinates. because it couldn't grasp the elegant polymorphism of the edge type deduction already in place.
So when the human developers finally realized this, what did the actual fix look like? Did they just highlight the AI's code and hit backspace?
Essentially, yes. They eradicated the entire node pairs layer. All 6 of those duplicated methods were removed, but the most crucial step was transforming how the tests operated.
Okay, how so?
Well, before the fix, the test callbacks were performing mental gymnastics to reverse engineer these synthetic node pairs.
And a callback, just to clarify for everyone, is essentially a function that gets passed into another function to be executed later, like leaving a voicemail asking someone to call you back with an answer.
Perfect way to describe it. So the developers updated these callbacks so that they simply receive the native edge data directly from the generator. No translation needed, no synthetic pairs. As the author of the case study points out so clearly, simpler tests directly equal fewer bugs.
Taking things away made the entire structure vastly stronger. And that leads us to the final act of this deep dive, the ripple effect. Because fixing this foundational AI-generated rot didn't just tidy up a single file in isolation. It triggered a cascading positive effect across the broader software ecosystem.
Yeah, removing technical debt at the foundation allows the benefits to propagate upwards. The case study details how a completely separate project, an upstream code base called NetOptim CIP, was heavily entangled in this mess.
So the infection had spread across project borders.
It had. NetOptimSave was actually the sole caller of that messy AI-generated fine nig cycle method. But by switching that call over to the elegant native Howard method, the developers were able to clean up an entire class called the Network Oracle inside NetOptim CP.
And an oracle, in this software context, being a component designed to act as a black box that answers a highly specific computational question. In this case, does a negative cycle exist here?
Yes, and that oracle became simpler, faster, and more direct. Furthermore, cleaning out this synthetic structure allowed the C++ code base to properly align with its Python equivalent.
Oh, that's huge.
Yeah. The code study notes that a component called the ratio class in the opt scaling oracle now perfectly matches its Python sibling. Unifying the architecture across languages drastically reduces future maintenance headaches.
So let's review the final scoreboard of this great deletion. Across both the digraph DAX and NetOptim projects, 11 files were altered. A staggering 241 lines of code were completely deleted from existence. In digraph XCP alone, the total test count dropped from 58 down to 45 because they were able to delete 13 entirely useless tests that were only guarding that imaginary redundant hallway.
Yeah.
And what was the operational result of ripping out hundreds of lines of core functionality?
Your regressions.
Unbelievable. The system didn't break, no features were lost, it just got significantly lighter and faster.
Exactly. All 32 tests in the NetOptim CP project passed effortlessly. The remaining 45 tests in digraph XCPP passed without issue. The only things removed from the repository were tests for code that no longer existed and code that should never have been written in the first place.
So what does this all mean when you zoom out from this highly specific 2026 case study regarding edge-type deductions in C++ graph libraries? What is the core takeaway for the listener?
If we connect this to the bigger picture, it forces a fundamental reevaluation of how we measure productivity in the era of generative AI. The tech industry has been deeply conditioned to believe that writing code is the job. We equate the volume of lines written with the amount of progress made. But the single most vital metric in software engineering is not lines written, it is lines maintained.
The true return on investment comes from deletion.
This case study proves mathematically that the fastest code to debug, the easiest code to review, and the most secure code you can deploy is the code that simply does not exist.
Wow.
AI coding assistants are powerful, transformative tools, but they require intense, skeptical human review. If you let them operate on autopilot, they will invariably create these parallel hierarchies. They solve local problems by creating massive global architectural debt.
Right.
We have to shift our entire engineering mindset from asking, did the AI write code that functions, to did the AI write code that respects the existing architectural blueprints?
That is the essential distinction. Because regardless of whether you are building a complex C++ routing library, using an AI to draft a corporate strategy document, or managing a massive logistics project, the core lesson translates perfectly.
It really does.
AI is an eager, unimaginably fast typist, but it is a historically terrible architect. It lacks a holistic vision. It will absolutely build you a confusing, redundant second hallway right next to the beautiful one you already have if you do not watch it closely.
And it will happily instantly generate a 100-page compliance report to prove that its unnecessary second hallway is structurally sound.
It is wild how persuasive that volume of output can be. Well, that brings us to the end of today's deep dive. But there is one final lingering detail from the source material that we really need to leave you with.
Yeah, in the future directions slide at the very end of the presentation, the author notes something quite sobering.
What's that?
While the development team managed to successfully clean up the C++ library, the Python sibling repository digraph_x_py still contains this exact same duplication.
Oh, no.
It still has both the elegant native method and the redundant AI-generated method sitting side by side.
So the shadow code is still there, quietly operating.
It is. Which raises a massive question for anyone building or managing complex systems today. If a simple AI assistant can quietly inject hundreds of lines of invisible, perfectly tested, yet fundamentally useless shadow code into just one specific graph library.
How much of our global digital infrastructure is currently being built right now on top of redundant, misunderstood, parallel hierarchies?
Exactly. How many invisible second hallways are being constructed across the internet at this exact moment?
And perhaps more importantly, how many decades is it going to take human engineers to finally untangle it all? A completely vital question for you to mull over as we increasingly hand the architectural keys over to the machines. Until next time, keep a very close eye on the blueprints.